Sure.
So today's seminar is about Chapter 2 in the oral textbook, and Chapter 2 is about multi-armed bandits. Multi-armed bandits are a way to explore the dilemma of exploration versus exploitation in reinforcement learning. This dilemma is something specific to reinforcement learning. To understand why this dilemma is specific to reinforcement learning, we need to understand how reinforcement learning is different from other types of learning. So, reinforcement learning is basically an evaluative sort of learning compared to other forms of learning which are more of instructive learning. When I say evaluative learning, evaluative feedback that reinforcement learning uses, it evaluates the actions that the agent has taken previously rather than telling the agent what is the correct action to do. So here the need for exploration arises because the agent needs to find the good behavior or the good actions to take. It needs to explore different options so that it receives the evaluative feedback and it knows which is a good action. So to understand the exploration versus exploitation trade-off, we use something called the multi-armed bandit, and here we are just going to use a very simple version of the multi-armed bandit, and it's going to be a non-associative case. What I mean by a non-associative case is that the actions that the agent takes is only within one situation. Okay? So,
can you explain what do you mean by one situation?
One state is what I understand.
Okay, let's go.
So let's talk about the multi-armed bandit case that we are taking today. So what the multi-armed bandit is imagine a slot machine. Like in casinos, you pull the levers and you get the jackpots. That is the slot machine, right? So imagine a slot machine with multiple levers. So it's a bad representation, but take this as a slot machine. And imagine it has 4 levers, okay? So each lever has some rewards to it. And the rewards have a probability distribution. So imagine 0.8, this is the probability, this is the reward, 0.2, 0.8. So this is the probability distribution of the rewards attached to this lever 1. And for lever 2, we'll have something similar. So the goal of this problem is to be able to maximize our reward in a certain number of time steps. Okay, so and a true value of this lever or this action A1 is going to be mean of this probability distribution, which is basically your probability x into p of x. Okay. So our goal finally here is to be able to maximize a reward where we are repeatedly faced with the decision of which action to choose in order to maximize a reward within a certain number of time steps. Are we clear till here? Right. So, and this value, this true value of this action is not available to the agent. So the agent does not know the true value of an action. Just try to imagine what will happen if the agent knows the true value of the action. The whole problem becomes trivial then, right? If I already know which action is going to give me the highest reward, there is no point of exploration or anything. I can just choose the action repeatedly of which one I'm going to choose. Like you're in a casino, you know which lever is going to give you the jackpot all the time. So I'm just going to keep pulling that lever. I'm not going to explore anything else. So the agent does not know the true value of the action. But in order to maximize this reward, the agent will have something called estimates. And the agent will take actions based on these estimates. So there are two parts to learning here. One is forming estimates, and the next part is taking actions based on estimates. Now let's look at what these estimates are. The true value of an action is represented using Q star of A, that is the true value of action A. Right. These estimates are an estimate of what this true value can be, the agent, and these estimates are represented by Qt of A. So this is the estimate of the true value that the agent has. Now the next part is taking an action based on these estimates. Now to form estimates we have three methods. One is the sample average method, incrementally implemented sample average, and the exponential recency weighted average. And to select your actions based on the estimates, we have 5 algorithms, which is the greedy, epsilon greedy, optimistic initial values, upper confidence bound, and gradient bandit. Now we're going to be looking at the first estimation method. So the first estimation method, the name itself gives us an idea of what it is. A sample average is basically the sum of all the rewards you get till that point T by selecting that action A divided by the number of times you've chosen that action. So it's basically sum of rewards of action A divided by number of times A is chosen. This is your sample average. To represent that mathematically, we have sigma I is equal to 1 to T minus 1 till that time step, sum of all your rewards I, and I'll explain what this part is in a minute, divided by the sum of number of times you have chosen A. So this, we've just represented it mathematically here. So this part is just a random variable which becomes 1 when this predicate is true. So when calculating a sum, when you're iterating over different rewards of different actions, whenever this reward is associated with this action, this value becomes 1 and it is considered in the sum to calculate. Are we clear there? Okay. And this sample average, when you ultimately we want, this is your Qt of A. So we want this value to be as close as possible to the true value, which is Q star of A. Okay. Now, once we have an estimation method, what is the next step? The next step is to select an action based on these estimates, right? So let's look at the first one, which is the greedy action selection. Now, suppose you have, after the estimation, suppose you have values such as 0.8, 0.5, 0.2, and 0.3. Suppose you have your estimates like this. Now, what is the most obvious thing without trying to optimize? What is the most obvious thing to do here? Is to select which action?
A3.
A3, right? Selecting the highest action is basically the greedy algorithm. Okay, so selecting the greedy, this is called the greedy value. So selecting the greedy value is called the greedy algorithm. But there is a problem with greedy algorithm. What happens is, you've tried out all these actions once, A1, A2, A3, A4, and you formed some estimates, right? And you know this is the highest based on one trial. Always remember that every time you estimate, there is always uncertainty attached to that estimate, right? There is some sort of uncertainty about how good your estimate is, right? So when you are repeatedly choosing only action A3, you are not exploring other actions which might give you more reward, right? That's why when you're repeatedly exploring this, you are not always doing the optimal action to maximize your rewards. So in order to explore other options, you are considering something called epsilon greedy algorithm. What epsilon greedy algorithm says is, select the greedy option for most part of the time, but for epsilon percentage of the time, select any of the non-greedy options. Okay?
Can you repeat again?
Yeah, in greedy what happens, you're just selecting the highest action with the highest estimate, right?
Mm-hmm.
But what is happening there, you're just exploiting based on one trial of the actions. So you don't know if these will give you higher rewards, because there's also uncertainty. I'm only say 20% certain that it will give me a value of 0.2. As I try action A1 many number of times, my confidence will increase to maybe 80% that it will give me 0.7, right? So when I'm just selecting the high action associated with the highest value, I'm not exploring other options which might give me a higher reward. So in order to encourage some exploration, what I use is the epsilon greedy algorithm. There I tell the agent to select the action with the highest estimate for most part of the time, for like 90% of the time. And for 10%, that is the epsilon is equal to 10% of the time, I ask the algorithm to select a non-greedy option. Right? A non-greedy option is an action which is not associated with the highest estimate. Okay, so then what happens is, as it tries out other options, it might find an action which is giving it higher reward than it previously thought. So when we compare, before we compare these two, we need a method to benchmark these algorithms. So to benchmark these algorithms of how they are performing in relation to each other, we are going to use test bed. This test bed is going to contain 2000 slot machines, with each slot machine having 10 arms. And we're going to be using 1000 time steps. Right. So what this means is, this is a big set of 2000 slot machines, and you're going to run each algorithm on each of these slot machines for 1000 time steps. So when you're running each algorithm in each of these slot machine for 1000 time steps, that is called a run. So we're going to be making 2000 runs for each of these algorithms in order to get a view of its performance. So if you look at page number 50, the 10-arm test bed. Everyone on this page?
Yeah.
This is the figure. Yeah. So this is the test bed we're talking about. So this figure is just showing one slot machine, right? And these are the 10 arms that one slot machine has. And the action values have been selected using normal distribution with a mean of 0 and variance of 1. And the rewards have been selected with a normal distribution with a mean of Q star and a variance of 1. We will get to what they mean a little later on. So this is basically a test bed. Now when we run the greedy and the epsilon greedy algorithms on this test bed, these are the results we get. Go to page number 51, where you see the epsilon greedy with epsilon values of 0.1 and epsilon values of 0.01, and the greedy algorithm compared in this graph. Do you see this graph?
Mm-hmm.
So here we can see that the epsilon greedy, where it just selects the highest value based on its first estimate. So that one improved fast, but after a certain point, it just flattened out. So its average reward is just 1, whereas the maximum possible reward is 1.55. The other epsilon greedy algorithms were able to get to that maximum of 1.55 by exploring the other options. Okay. Now, consider this scenario. Suppose my reward variance is very low. Which algorithm do you think will perform better, the epsilon greedy or the greedy algorithm?
Sorry?
Suppose the variance for the rewards is very, very low. Which algorithm will perform better, the greedy or the epsilon greedy?
Greedy.
The greedy algorithm, right? So when I say the variance is very, very low, it means that my estimates are going to be very close to the true value. So when the agent already knows the true value or very close to the true value, then the greedy one does better because it's going to exploit the greedy option. Whereas the epsilon greedy is going to be performing suboptimal options for the most part of the time. So it's not going to be as good as the greedy one. So the advantage of greedy or epsilon greedy depends on the type of problem you have. In the problem, if you have high variance, then the epsilon greedy would do better, and if it's a low variance, the greedy would do better, obviously. Now we'll look at the second estimation method, which is incrementally implemented sample average. See, when you are calculating the sample average here, so every time you get a new reward and every time you are choosing that action one more time, you are going to be adding one more memory to store that value, right? When the fourth time you select action 1, you need to store the reward here and you need to store the number of times. So it's not memory or compute efficient. To make this calculation of sample average more efficient and do it in a constant time and constant memory space, we are going to use the incrementally implemented sample average. And we're going to derive that from the equation of sample average. So your equation of sample average, Qn minus n plus 1 is 1 by n I equal to 1 to t. Alright. You get this part, right? So it's the sum of all your rewards till time t divided by the number of times you've sampled. So from that you can write it as 1 by n Rn, which is the last reward that you get, plus sum of I equals 1 to t minus 1 Ri, rewards till then. Here? You can then write it as Rn plus, I'm just going to multiply and divide with n minus 1. N minus 1 into 1 by n minus 1 epsilon I equal to 1 t minus 1 Ri. Now this part is the same as Qn, right? It's the same as this, so it's just Qn. You can write that as 1 by n Rn plus n Qn minus Qn. I'm just going to get this Qn outside, so it's Qn plus 1 by n Rn minus Qn. Now when you use this formula, the algorithm just needs to store the average of the estimate till that time step, which is Qn, and the number of times it has sampled that action. So now it is and then it needs to just do a small computation of adding the new reward to this. So now the computation is done in a constant time and constant memory. Can I press this? So we're done with this. Now, till now, we've considered examples where the reward probability has stayed stationary. Stationary means when I have L1, L2, lever 2, lever 3, lever 4, whatever probabilities I gave here stayed the same throughout the runs. Okay. Now let's weaken that assumption a little bit and say these probabilities change over the course, right? Like when it was 0.8 probability of giving 0.2 reward, now later it might change to 0.2 probability of giving a 0.7 reward. Basically the probabilities are not stationary. You can get a better idea like where you're in a casino and you finally estimated one value where you pull lever 1 and you're getting maximum number of jackpots, but the owner doesn't want to be robbed of his money. So what he does is he keeps changing the probabilities of the levers. So after 5 minutes, this lever might have the most probability to give you the maximum reward, right? So that's what we're imagining right now, that the reward probabilities do not stay stationary. In that case, if you're using sample average or incrementally implemented sample average, you are going to your estimate is going to converge with the true mean at one point, okay, and it's not going to change from then on. It's just going to exploit after that. But in this case, when your reward probabilities are not stationary, wouldn't it be a good idea to give more weight to your recent rewards than to the older rewards? Because the older rewards are in association to the older probabilities. Now the probabilities have changed. So it makes more sense to give more weight to the recent rewards when you're calculating the estimates. Right? Does it make sense? So in order to do that, we do that by using a constant alpha. A constant alpha. So we derive this from the equation of incrementally implemented sample average. So that is Q of n plus 1 equals Qn plus 1 by n Rn minus Qn. This is our incrementally implemented sample average, right? In this case, this is the alpha. We'll talk more about this a little later. Now, to derive the exponential recency weighted average from here, let's just replace this part with alpha as Qn plus alpha Rn minus Qn. This can be written as alpha Rn plus 1 minus alpha Qn, alpha Rn plus 1 minus alpha into, I'm just expanding this Qn formula here, where I say alpha Rn minus 1 plus 1 minus alpha Qn minus 1. Alpha Rn plus 1 minus alpha. I'm just multiplying these two terms, that's it. Into alpha Rn minus 1 plus 1 minus alpha square Qn minus 1. And so on. Now I'm going to expand this term too. Okay, just to show you the pattern of how it's going. Alpha Rn plus 1 minus alpha Rn plus 1 plus 1 minus alpha Rn minus 2 plus so on. So you see the pattern here. It's 1 minus alpha. The patterns in the power, it's 1, 2, and so for the last term it's going to be 1 minus alpha power n minus 1 alpha R1. And can you tell me the term, or can you tell me this part for for Qn for the last part? I'll just write it. 1 minus alpha power n Qn. That's going to be. And finally, you can just write it as 1 minus alpha power n Q1 plus I is equal to 1 to n alpha 1 minus alpha n minus 1 Ri. So this formula looks quite complicated, but I will just try to explain how to interpret it easier. So this alpha is your step size, right? When I used 1 by n as alpha in the incrementally implemented sample average, this alpha value is changing, right? Because the n value changes, the alpha value is changing. Here we are going to use a constant alpha, which is between the number 0 and 1. When we use a constant alpha and you are doing an exponent here, when you do an exponent of a decimal, it's going to reduce, right? So as the number of times you are trying out an action, the weight associated with that action's reward is going to reduce, because the older the reward gets, it has more exponents, right? It's being exponented so many times. So the older rewards are going to have less weight, and the present rewards are going to have more weight. So how this translates into the algorithm is, it makes sure that all the values are tried at least once, and that the recent ones are given more weightage. And this form of calculating the estimates is more useful in non-stationary scenarios, because this one doesn't directly converge to the maximum point. To make it more clear, you can take the example of gradient descent, right? When you have something like this, imagine a curve something like this. When you have a constant step size, say the step size is about this much. This step size is advantageous here because it overcomes the initial fluctuations. But as it does the gradient descent, from here it directly goes here. There is no point of actual convergence because it's of constant step size. If the step size reduces as it goes gradually, it will be able to come to the minimum, right? So here we are just choosing a constant step size, though, so there is no true convergence with the actual value of the action. So what that will make sure is that when your reward probabilities are changing, it is not converging to the estimate, but it is still sensitive to the new rewards that it is receiving. That is the reason we're using exponential recency weighted average. Now let's look at another action selection, which is the optimistic initial values. In the optimistic initial values algorithm, what we do is we set the initial rewards of all the action to a very optimistic number. So in this example, an optimistic number would be 5. So I set all the estimates for QT of A as 5, 5, 5, 5. Now just try to imagine what happens here. I have an algorithm which has to select amongst these options, right? When it selects this action, it's going to get some rewards which is definitely lesser than 5 because we chose a very optimistic value here. Suppose it gets a reward of 2. Now when it makes the next selection for the next time step, it's going to select one of these actions because it is going to be disappointed with this reward in comparison to its original estimate. And when it selects this action, again it's going to receive a disappointing reward. Hence this pattern continues until it gets proper estimates. So this optimistic initial values basically encourages more exploration because it is dissatisfied with the rewards it gets compared to the optimistic values that we've associated. And you can see that graph on page 56. When you look at that graph, you can see the blue line is for the optimistic greedy algorithm. So that one is not performing well in the initial time steps because it spends most of the time exploring different actions rather than exploiting. But once it is done exploring and finds a good action to take, then it performs well and it is exploiting the highest estimate that it has. Any questions here?
Can you explain the spike in the figure 2.3? There is a spike in the optimistic greedy.
Just give me a minute. I think it may be by chance because it is maybe one of these actions is giving the higher reward. I'm not completely sure.
Okay, go on. I think it is when you cut many values at the same time, then there will be some coincidence where you achieve a biased version of higher reward.
Yes.
So this is if the reward was like 1, 2, 3, 1, then this optimistic initial value begins from the 10 and it decreases, and at some point it goes like 2, 4, 6, 2, things like that. So somehow it arrives similar optimistic value. Can you write it down? 2, 4, 6, 1.
Okay.
That's 2, 2. 2, 4, 6, 2.
Okay.
Yeah, so it's when the system performs well, but still this value is biased, so it continues changing and the optimal action decreases. So that's why after the spike, you get the lower optimal action again. So,
So you're telling the action that was very close to the optimistic assumption was in the center, so there's an increment and then the other values are again decreasing. Their estimates are lesser than. So the values increase and go close to the optimistic realization and then start decreasing again. And that's why this.
no. I couldn't understand what you say, so can you say?
So there are optimistic values on top, right?
Optimistic values.
This is 5, 5.
Yeah, let's say.
And the estimation for each action is increasing and going close to the optimistic value and then decreasing value.
No, these are the estimates.
So, Sanas, you do not understand the optimistic initial value. You totally reversed it. Right? It does not increase. It is always decreasing.
This is a reward value which will never be achieved.
No, I got that. I'm not telling that. So you're writing the 2, 3, right?
2, 3.
Like for the first one. First row is all what your optimistic value is 5, 5, 5. Then below what estimates are there that you achieve is 2 for the first action 2. And then 3. Maybe the next one is 4.4 and then 3 and then 2. Maybe because of that the graph is.
So,
I didn't tell the optimistic value increases, your estimate of those values.
No, even the estimate.
In the sense, not for an action. Maybe there's an action that is. So even if the next one gets 4.4, I mean 4 as the reward, right? It's very close to the optimistic value, but you still won't choose it, right? You'll go to the next one.
No, you'll go to the next one.
Right? And that one, if it gives a reward of 2, now you have like a increase and decrease in those values. I'm not telling.
No, I don't think this is the one which is reflected here.
So it's exercise 2.6 at page 57. So everyone think about what this situation happened and post their opinions on Slack. Okay, after the seminar, think
Okay.
about the issue and post your opinions on Slack. Okay, I think the time is up. So we will continue 4 and 5 next week.
Okay.
Okay, and everyone, I think the first chapter 2 and 3 is